Today we're going to look at language extensions. So first of all, what is a language extension? And to understand that, you have to know that Haskell is just a specification. All programming languages are just specifications. And language specifications, they kind of want to do two opposing things. They want to have all of the newest features. They want to be this sort of pit of innovation and research. And the Glasgow Haskell compiler really has that. But they also want to be stable. Because if they're not stable, they won't be used in industry. They won't have investments put into them. They won't end up with a user base because it changes too much. It's too complicated. And Haskell really does actually manage to hit both. And the reason is because it has both a specification and then this ability to add extensions. So we've been using the Haskell 10 specification, 2010 specification. You can actually see if I open the Cabal file, we've specified it down here. But we can also add extensions to it. And that is a feature of the Glasgow Haskell compiler, GHC. But there are other compilers, believe it or not, that actually implement the Haskell 2010 specification. Maybe not fully, but they're working towards it. GHC is not the only one. But yeah, no, you can add extensions, and people looking into compiler design, they often add extensions to Haskell. So a way of adding extensions, if you want a language extension to be applied across all of your Haskell files, you can do it here. You can go default, extensions, and then you can list them. So we could say overloaded strings, for example. We could have more, view patterns, etc. But that's not used so often. I use that sometimes. I use that often with existential types, which we'll get on to, because that kind of has a ripple-off effect. But you can actually just apply them to a single file. And that's what we're going to do. I don't need to save that. Okay. So a normal way, or a very common way of adding a language extension, as you will have seen us do before, is to add language. Add this at the top. So you say language, and it's inside a curly bracket, a dash, and a hash. Language, and then overloaded strings, for example. And that will enable the overloaded strings language extension. Now, we've only done it to that file, bear in mind, so we haven't done it to the REPL. So when you want to add something to the REPL, you either have to do it by default in your Cabal file, or you can do it like this. You can go set-x, and then your language extension of choice. So we now have overloaded strings enabled in both in our REPL and in our file. But anyway, we've actually been over overloaded strings. We know what it does. It allows people to overload what these string constants mean. I'm going to go over some more interesting ones today. So let's start with pattern synonyms. Okay, this is one of my favorites in conjunction with another, and I use this all the time. So pattern synonyms allows you to define a pattern outside of the function where you're actually doing the pattern matching. So the way you do that is you go pattern, and then you might go list. So I've now defined and it just looks like a constructor, but I've described this pattern, and it's going to equal x cons x's. This is a really bad example, but sometimes when we're talking about Haskell, specifically when you're trying to make Haskell tutorials, you want to show that list is a type like any other, and you define list in this sort. But if you define this, then essentially you can use your sort of fake Haskell definition and make it an alias of the real one. So empty like this. No, empty like this. Great. So now I can define a function, count, say. So this is how you'd normally define it. So that's going to count the elements of a list. So if I go count 1, 2, 3, oh, spelt it wrong. It says 3. But I can also now use my pattern synonym. So I can say empty. List x x's. and it works in exactly the same way. Fun. So what I normally use this in conjunction with is view patterns. That's what it's called. So let me show you another one. So view patterns, there it is. So view patterns allows you to add a function into the pattern matching section. So say we wanted to add one to the head of a list. So that was our function. Add one head. I could, if I wanted, I could say x-axis equals x plus 1. I could do it like that. And that is actually exactly how I would do it in real life. Fine. But I could also use view patterns, which means I have a function. So the function is head, and whatever I pass into this, which in this case is a list, it's going to go through this function, and then I pattern match it on this side of the arrow. So this is exactly the same function, and it works in exactly the same way. But the cool thing is when you use these in conjunction. You've heard of cons, the connecting constructor in a list. We sometimes say snock, and snock is sort of a backwards list. So something you could do, yeah, I'll write it and then explain it. So what we're going to do is we're going to have a pattern synonym, and we're going to use view patterns inside it. So we're going to say snock x's, and you see I've got this here, this arrow here, and that means that it's not a two-directional. They're not equal. This one turns into that one, and that's going to be reverse going to x's. Okay, so this is a pattern synonym. A lot's happening here, but essentially the list comes in here, it gets reversed, we pattern match on x's of the reversed list and put it here. So I can say this, last equals snock x's x. So it looks like I have this backward list type, but I don't. It's just a pattern synonym for a function. So it's quite powerful. Oh, I've got an equals where I shouldn't. Let's have a look. Oh, and I've spelt snock wrong. There we go. It's cons backwards. Good. So last of, yeah. Oh, there's already a last in prelude. I need to call it last prime. There we go. So we're sort of pattern matching on the reversed list. Great. So those are two of my favorite language extensions. I use them a lot when I'm writing a compiler, not an interpreter, and I need to do optimizations. I use view patterns a lot to manipulate abstract syntaxes of the output language. So that could be C, that could be assembler, that could be sort of an intermediate language. I use that to just look at them differently to make writing optimization code easier. So that's one use that I use a lot. Good. So what should we look at next? Let's look at multi-parameter type classes. Let me get rid of it first so we can show the error. So what you sometimes have, you have a situation where you want a type class to act on more than one type. Let me give you an example. Let's define a class, loose eq. And I've completely stolen this from the internet, this example. Just so you know. This is not my own work, but still. Loose eq ab. Now, you can think of this as maybe we want to compare integers and floats. So 1.0 is equal to 1. We want some kind of equality that's going to help us there. And so we define this class loose equality when we have the function loose eq, That's what they use on the internet, but I'm going to make it infix because infixes are cool. Which is of type A to B to bool. What we'd want is we'd want an instance of loose EQ of int and float. Whoops. Where I don't need that, equals kind of B equals A equals round B, for example. And we want it the other way around as well. So instance loose EQ float int, because we're going to have at least transitive, symmetry. We want our loose equality to be symmetric at least. So A equals B equals round A equals B. Okay, and this is not going to work. And the reason why is because we don't have enabled multi-parameter type classes. But I wanted to show this for a reason, which is Haskell often tells you, or GHC often tells you, if you've written something that needs a type class. So often you don't actually have to remember all of these names. I certainly don't. I just type and Haskell tells me what I should have enabled. So when I enable this, oh, I've spelt round wrong. There's always a spelling mistake. And we can say things like 1 equals 1.0. Oh, it thinks that's a double. Thanks, Haskell. Oh, and it thinks that's an integer. Well, this has gone badly. There we go. True. But if I say that's going to be false. But if I get a really close one, you know, yeah, good enough for our function. So that's one use of multi-parameter type classes, and you see them popping up all the time. There's also something called functional dependencies, which allows you to specify, we won't go into it much, but you can say things like, that's not here, it's in our class definition. You can say things like this, which is for every A, there's a unique B. And say we had another thing here. I could say things like, for every AC pair, there is a unique B. And that's pretty much it for functional dependencies. I see them cropping up less, but sometimes they are useful. So I've given you some rather easy ones. These ones, although sometimes a bit weird to wrap your head around the syntax, they are just sort of very efficient, quick ways to sort of make your code more clean. We've kind of made Haskell slightly more expressive with the multi-parameter type class. But yeah, they're not so difficult to get your head around. But there are some which are more involved. So we'll start with generalized algebraic data types, or GATs. This one introduces two things. A, some syntactic sugar, and B, type equality. This is type equality. So this is true if A and B are the same type. And you're probably thinking, why does that matter? And it's because you can express some really interesting things. So for example, maybe I'm defining an interpreter, but this time I have a parameter A, which is the return type. I can say things like where A is equal to bool, I think that should be in brackets, bool const A. I'm going to do it like this, and then I can say where A is equal to int const A. And then I can say where A is equal to int again, I can say add is of type expression A. Yeah. Yes, so what we're saying here is we're saying that a bool constant can only have a bool as a return type, A is equal to B, bool. And an int const can only have A, int, as its return type. It's only an integer. But our eval function can be of a really interesting type. It can be of a type expression A to A. Okay? And we can write things perfectly validly, like bool const b equals b. Eval int const I equals I. Eval add AB equals eval A, I'll bracket that, plus eval B. That should type, yes. But that's so weird. One line is returning a Boolean, and one line is returning an integer, but it doesn't matter. It understands because here A is equal to Boolean, and here A is equal to integer. So we can kind of work it out. So this is, although a really rubbish and simple interpreter, it is type sound by construction. But nobody really likes writing it like this. What we have instead is we have a much better syntax. And that is the where syntax. Now, if you remember, constructors are just functions. We could build a type just by defining its constructors. So I'll give you an example, an easier example to start with, and that would be list. So what is the type of the empty constructor? Well, it's just of type list A. Okay. And what is the type of the cons constructor? Well, that is of type A to list A to list A. And that's it. That's our type. Types and all. Because, you know, I build a list by saying, you know, list equals 1 cons 2 cons. Oh, they should be capitals. I apologize. Empty, for example. You know, that's just a list. That's the list 1, 2. And they are constructors, which are just functions. And we defined this just through no instance for, I forgot some brackets, I apologize. Yeah. They're just constructors, are just functions. There we go. So back to our more interesting expression type. I know I said interpreters were over, but interpreters are everywhere. You have to put up with it. We can say that our bool const is of type bool to expression bool. I think that's a lot easier to sort of visually see. I can say my int const is of type int to expression int. Add is of type expression int to expression int to expression int. This time I will do the if. The if is of type expression bool to expression A to expression A to expression A. Because you see both sides, the true case and the false case, they all have to match the return type. And that'll type. And now I can write, I can write eval functions that include quite a complicated if clause. If condition e1, e2, I can just say if eval cond, then eval e1, else eval e2. And that's ridiculous because that types, it knows that this will be a Boolean. And it doesn't care what these are, they're of type A. And that, not in scope. Oh, is it because it's indented? I know, it's because I forgot the eval. Yeah, that types just fine. So it's a very, very cool language extension. So next, let's look at, and we'll stop soon. I'll probably continue this on to the next video as well, a few more. Let's look at rank n types. So rank n types, they're surprisingly useful. So someone starting out at Haskell might write, and I must say I've actually stolen this from a book, this example. The book is in front of me and called Thinking with Types. It's well worth your read. So someone starting out at Haskell might want the function apply 5. Okay, and it's of type, takes in a function, a to a, and it returns an integer, and apply 5, f equals f5. And their thought is, well, the function is a to a. It's not for a fixed a to the same a. They think, oh, it's just an a to an a. And of course, it doesn't work. It goes, we couldn't match int with a. Because what they were thinking of is for all a's for every single a to a. And what we are allowed to write in Haskell with the rank n types enabled, I'm not going to go into the difference between all of the different ranks. You can look that up yourself. Is we're going to say something like for all a, like that. Oh, have I bracketed everything wrong? I think so. There we go. So now, if I look at the type, apply to 5, you see it's for every single a to a. So we can say things like this. Apply 5 ID. Because the type of ID, if you look, it just says a to a. But yeah, I guess if something's type is a to a only, then it is for all a to for all a. And there you go. I think that'll be it. Next week, we're going to look at more type-related ones. We're going to look at data kinds, maybe polykinds, I don't know, type families. And that is laying out the foundation. Then we'll have enough type knowledge to sort of look at making our own version of servant, which is the that's the library that we're going to use to make web stuff. Good. That's it for today. See you next week for more language extensions and then some really useful Haskell.